of lecture. Okay. Next time you do it day before, right? So that they will be free as a bird to come to the lecture. Good. So let me remind you what in essence, we are doing. Technically speaking, we're studying communication theory, but really deep down, we're learning to see everything as a message. And this more or less will be, like mental exercise, which is sometimes easy, for example, as we discussed, when we have some B, and this is a part of a source or natural world or phenomena, and we receive, measure quantity which is A, which could be vastly from a different domain, then the quality of this measurement, which we will call channel, transmission channel, it's measured by the information that it brought. Before we get measured, the uncertainty was S of B, entropy of the distribution of all possible values of B taken with their own weights. And after the measurement, we had a conditional entropy. And that what is we call information on average brought by this channel. And this is called mutual information. Now, we ended last time by noting the symmetry, which follows from a very trivial statement, which is called chain rule. And we'll be using it over and over again. So let me a little bit elaborate. When you have two independent probabilities, P of A and P of B, then their joint distribution is just a product. And of course, their entropy is a sum. When A and B are correlated, still such a product rule works. Namely, you say that the joint probability of A and B could be written, somehow it's written from the right, as a probability of A times probability of B under the probability of A. Just the same, we can write it as a probability of B, somehow in a Hebrew way we read it from right to left, as a probability of A conditional on B, right? And then in this case, again, the entropy S of A and B could be presented as S of A plus S of B under A, which is the same as S of B plus S of A conditional on B. This is called chain rule. It's kind of a standard chain rule. But now, again, I can just take this with a sign minus here, take this with a sign minus here, and see that S of A minus S of A of B is equal to S of B minus S of B of A, and this is the mutual information of A and B. Okay, so it's trivially symmetric. It's a degree of correlation between A and B. It does not care which way you transfer information in this channel. And it's a very useful quantity, and we now start applying it to different things. And in particularly, Shannon suggested to measure the quality of a channel, and that's what we ended last time, by the quantity which we call capacity. And capacity is defined as a maximum taken over all P of B's of I, A, and B. Now, generally, I mean, this mutual information depends on the statistics of B, right? Yes?
Sorry, when you say maximum over P of B, you mean over the entire family of possible distributions?
Over all possible normalizable distributions. Okay, just all possible. Of course, you always work in a given class, namely that you assume that it's discrete out of, I don't know, m values. in a moment we'll start working with continuous distribution as well. And then again, it's a right remark, in a sense this capacity depends on what class you are working on this distribution. But then again, when you compute this must be computable for every member of this class. All right? So if I take n values, this is my b, and it runs from 1 to n. Okay? But when I measure a, I do not distinguish. There is always m so there is 1, 2, etc. So this is the typical, I mean, the simplest, and this is even without randomness. So it's kind of just for example, with my resolution, I cannot distinguish between these different possibilities of B. What is I of AB in this case in terms of number n and m? What is S of B? What is S of B? We need to take maximum, right? So we know that maximum of, because of convexity, is a uniform distribution of probability. So this is just a log of n, that number of bits. And what is this? After we receive A, how much uncertainty remained? What are, how many choices of B? Don't be shy. You know the answer, right?
I mean, there remain n choices.
For every value of A, this is the entropy of B conditional on A. So if I know A, how much I don't know about B? How many uncertainty remains? M numbers. So this is minus log 2m. And this is a log 2m over n. Okay? Now, turn the tables. Assume that you are actually able to receive n values of A from 1 to n. But what actually happened is that these different values all correspond to the same, and again, you know, if you experimentalist measuring things or doing communication, those are two vastly different situations, right? In one, you have many things, you just don't have enough resolution to measure them. Now you can actually distinguish a lot of things, but they aren't meaningful. You know, all these values that you measure, they aren't meaningful. It's only the whole group matters. So it's 1, 2. Again, what is the capacity of this channel?
Actually, I have a question.
Yes.
About this setting. Sorry.
Yes.
Like for the left setting, I understand that we can just like consider this as the mapping. But like the right setting, the mapping is like not defined. Like it is like ill-defined mapping. So
You mean you obtain signals like 1, 2, 3, 4, 5, and they all correspond to the same input, right? It happens, you know. You have a noisy channel. Whatever happens, you know, just can add random numbers with. I mean, we'll see examples. I mean, both this and this can happen just equally probable.
so for the right case, we consider like it is decaying for each of the probability.
Here, it's one of the examples. There are many realizations of this. This is, you can say, this is like I don't have enough resolution. So this guy is just kind of tiny things. But this, I can say that this is what I receive. But on the way, there is a noise. Noise adds and give me out of this number all these possible things, because it can randomly add a little bit of noise this way or that way. This one could also add a relative noise. Fortunately, we start from a simple case. Those are distinguishable groups, right? Then what is the mutual information and capacity in this case? Again, I have n values of A, and for each value of B, I have m possibilities. Let's compute it in two ways, okay? So, for example, compute it here as S in this way, S of B minus S of B of A. What is S of B in this case? How many values of B?
N over M?
It's log n over m, okay? Now, what is the entropy, conditional entropy of getting B if I know A? 0. For every value of A, I exactly know which B will be. Right, for this value, for this, I know that it will be this one. Minus 0, so it's the same value, right? Look from the other side, it's S of A minus S of A of B. Now this is log n, and this is log m, okay? So whichever way you look, okay, it's still, but then again, when we write this formula, we assumed that we are really computing not mutual information, which depends on the statistics of B. I can choose different ways, but capacity, which assumes maximization over the statistics of B. And in this particular case, maximization is trivial. It's just taking uniform distribution of B. Okay, good. Let's now ask a little bit more sophisticated question. Is that where is my picture? Yeah, here we are. So now, no, that's not. Where is my eraser? Here it is. So now I want it to be like this. 1, 2, 3, 4, 5, 6. 1, 6. This is my B. This is my A. It also has 6. Okay? But we'll do it like this. Imagine I'm on a torus, right? So, yes?
Should there be 2 lines from each on the left?
There are
The second from the
1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This with 2, there must be 2 lines. Yeah, that's a totally superfluous lines. Absolutely, yeah. So now we have, again, a symmetric situation. From the viewpoint of communication, it's a total nightmare, right? Because it means that, I mean, for which way I look, I don't know exactly where it comes. There is always 2 possibilities. Okay? So I am asking what would be the mutual information and then the capacity of this channel. Again, I mean, you know the formula, right? It's it's kind of not a big deal, right? So if I take S of B minus S of B minus A, what is S of B? Yeah?
Like log 2 and 6 or
Yeah, if I take them kind of uniformly, then it is a logarithm of what? Of number, which is 6, right? And then if I know A, what remains unknown about B? 2, which is minus log 2, which is log 3. And this, in a sense, gives you the following interpretation. The capacity of a channel is a logarithm of a maximal number of distinguishable signals, which means that I can, of course, consider it like this, but can I say, let's take probability of B the following. P of 1 is 1/3, P of 2 is 0, P of 3 is 1/3. You got the drill, right? So I'm using these inputs, not all of them. I'm taking probability, so this is 0, and this I never use, and this I never use. Then I would have signals which would be with 1-to-1 correspondence having logarithm of 3 entropy, right? So capacity is a logarithm of a number of distinguishable channels, and in this case it's okay. But really, again, it's important that it's a maximum. So when I eliminated every even channel 2, 4, 6, I need to take the remaining with equal probability. That would give me this maximal entropy, which in this case will be information transmission rate. Okay. Okay. Now assume that we really now these are trivial examples in the sense that kind of relation are fixed, namely that this always give me this or that. But in reality, it could be errors of very different nature, right? So this could be give me this or could be give me that, etc. So really, and that's what I'm not going to prove you noisy channel theorem by Shannon. If you're more mathematically oriented, you can take cover Thomas book of information theory, let's say, or go to original paper, which is pretty readable. But I'll give you a meaning of this. So what Shannon said and why this quantity is so important is that he proved in a pretty general case, unfortunately non-constructive, namely that he did not show how to find this. But he says that you can always write a rate of information transfer, so that the probability of error, well, if we're in bits, then it will be always 2. So if you take your rate, however smaller than your capacity, then in the limit of infinite n, your asymptotic probability, this is error probability. It goes to 0 exponentially with this difference, right? So actually, the capacity indeed establishes a maximal possible rate. It's never achievable because in this rate, your entropy of error does not decrease. Question? Yes.
So this, if it so happens that C is less than R, then this will blow up really quickly.
Absolutely. Absolutely. You try to exceed your capacity, you even approach your capacity. And that you would, because that's what, why it was so intuitively difficult and why you need a genius to do such things. Because the idea was, okay, let's make really long messages and then we'll exploit statistics. But people were saying how it would help. Your channel continue to make errors. You make longer messages, it continues to make errors, right? And that's what essentially this proof is, that it's you can. This is really the way. And of course, technically, it's very, very difficult because you need to develop error-correcting algorithms. And this is non-constructive. This is just the mathematics, which tells you that something exists. I remember when I was much younger, I derived some formula for some probability density distribution. I was very proud. And then my friend invited me to the talk of French mathematician, very, very famous mathematician. He said, this guy proved that this object exists. I say, what the hell? I mean, I just computed it, you know, in Bessel functions. I mean, he said, no, just go and listen. And of course, when you listen to a mathematician, you understand that, you know, finding something given as a theoretical physicist exact formula does not mean that you know what you're talking about. The mathematician explains to you what is actually that you and where is the boundary of it and all this. But of course, this is non-constructive. Now, let me give you kind of the feeling of argument where it comes from. It tells you, for example, let's consider a very particular, but in a sense, so imagine that we have a binary channel, just that simple. 0, 1, 0, 1, but it can make errors with a probability q. Okay, so you can just, which means that what you now have is that the probability of 0, 1, it's a conditional probabilities which we need to compute. It's q. Probability of 1, 0 is the same. It's q. Probability of 1, 1, no matter what a or b, in both directions is 1 minus q. And this is also probability of 0, 0. Okay, so now we can compute what is S of A of B, which happen to be S of B of A. It is this entropy of making this error, namely that for every this guy, I do have this probability which is the probability which is q1 minus q, and its entropy is what we'll call S of q. It's minus q log q minus 1 minus q log 2 1 minus q. That's a standard probability. Now, to get a capacity of mutual information, we need to take the entropy of input or output, they're the same. What is the input? What is the maximal entropy of a 1-bit channel? What is the number equal to 2? 2. What is the entropy of 1-bit channel? 1 bit, yeah? Just by definition, it transmits 1 bit, right? Until we start making the mistakes. So our C in this case is 1 minus S of Q, right? Or S of B minus S of B of A. Or S of A minus S of A of B. Okay? And this is its capacity. And it's interesting to plot it as a function of Q. That's what every communication engineer knows, just, you know, wake him in the middle of the night. So where it's 0, for which Q? Where we totally unable to use this channel, capacity is 0. Yes? 1/2, of course. When it's with probability of 1/2, that means there is no correlation between input and output. That's it. So it's right in the middle. Of course, when Q is 0, then it's unity, which means it's a perfect 1-bit channel which has a capacity 1 bit, right? So it's 1 over here. And of course, when it makes mistake every time, it's also perfect, right? Good, so we know, just, you know, when somebody says yes means no, somebody says no. Yes, question.
Slightly stronger than that, it's symmetric around 1/2 point.
Of course, it's symmetric around 1/2 point. There's kind of, you know, the moment we know that it kind of switch. So of course, it's a symmetric function around half. And of course, it's unity also here. And it's such a function. It's actually very sharp here. When you have like 10 minus 3 q, it's you have 0.998 capacity. So you're very close to 1 bit. Okay. So this is your capacity. Now, for every so now if you have again our favorite object of study, namely strings of 0, 1, 1, 0, 1, n string, we know that there is q n errors in it. Just we know it. That's how Shannon actually used this argument that you really need a limit of large n. That in the limit of large n, you know how many errors there are. What we don't know, as usual, is so we know the number of errors. That's good. That's good news. What are the bad news? What we don't know? Where they are. Exactly like, remember when we were getting out of Boltzmann entropy Gibbs entropy, we need to know, so our error corrections and whatever must be not less bits than there are possible positions of errors, right? Which are, of course, will be n factorial divided by qn factorial divided by n minus qn factorial, which is 2 in the power n s of q, this s of q. I don't derive it by Stirling formula, you've already seen it ad nauseum, right? But essentially it tells me this is the total number of possible positions of error. And so I need to send also some m error correcting bits. Again, it's non-constructive, right? But it's something which at least tell me where it would go, and so that the number of possible configuration of the thing will be 2 in the power m, and this must be larger or equal than this. If I really want to correct, usually it's a lot larger. But what is really important here is not that this is like 5 times less, that it scales the same with n. Because we are talking about 10 to 12 bits per second coming through any cable in this building, right? So we are talking really big numbers. And that's why I start working. So essentially, when we say that this is like this, that we say that m must be larger or equal than n s of q, right? And then the transmission rate, which is n minus m now over n, right? So it may seem that the transmission rate is 1 bit per symbol, but it's not, because some of these bits are totally information free. Well, they are error correcting, but they aren't message. So this is the rate with which you send message, and this is less or equal than 1 minus s of q, which is your capacity. Okay, so this is not a proof of Shannon's theorem. It's a physicist understanding what it's all about. So why it is, well, you lower rate, and of course, the less probability you want, you need to lower your rate of information transfer, because you really, okay? Questions? Yes, please. M is a number of error correcting bits. Something which is not related to the information that you transfer. For example, you say that I would send it in a column, and in every column the sum of it is 0. Well, numbers. Let's say you say 1 minus 1, or the sum of it is 5, which means that in every column there is more than 5 ones. Maybe, okay? So there is some error correcting codes which use some kind of prescribed rules, and they send you message which is only related to checking errors. Because if you find that some sum is not prescribed number, you know that in this column you have an error. Okay? So m is a number of bits sent on error correction. And it lowers your rate of transfer.
Those are not noisy bits.
Huh?
Those bits are not noisy, or they don't have error themselves. So for example, if I'm sending down m additional bits down a channel, I assume that there will be some error on those bits as well.
Yeah, absolutely. Of course. So they That's why it's really that's something which you try to make a self-averaging quantity. So in a sense, again, I'm not an expert in it by far, right? But the way that I understand it, particularly what I mentioned, that you use error correction things which are related on some sums. Not that you say that, I know, on my fifth position is actually 1. Maybe on the fifth position you didn't make it, and maybe in this message you gave an error and it had not the fifth and sixth. You try to do your error corrections which are related, which are spread. And then on average you diminish the, because even when there is something which is wrong there, but because you have m large of units there, then you can still read it correctly. But of course it's an art, and then it's something which you may have, something which would be probability behaving not linearly with n, but like lower power, which is again asymptotically you would be okay, but on any given large n you would have n, square root of n, number of errors because of error correction, etc. It's a complicated engineering thing, and you know, people spend billions on it. But the idea is here, and it tells you, and it shows you the engineering part of this mutual information. Yes?
Can you see it from scaling? If I take a few channels and say this is one channel, the information that's going and combine it in groups, would I see this, the capacity of the channel through this
No.
renormalization group or something like that?
Yes, there are some things which you really try to do in parallel transmission. So in a sense, your transmission goes in many channels, and in every channel you can make an error, but you do your error correction in this way. Okay? So you see that at every step, somehow you prescribe some property. For example, this would be even number or odd. Okay? So then, which means that as the stream of data goes, you don't check like this. You check like this between different channels. So there are many tricks here, and I am the last person you want to listen about, you know, there is so much human ingenuity put, you can imagine, right? But still, it's all based on this idea that the rate of transfer is your entropy. The rate of maximal rate of transfer is the mutual information between this and this. To take maximum of it, to take capacity, you need to choose the statistics of input so that it would be distinguishable input from the viewpoint of your output. And then if your rate is lower, asymptotically you are okay. So that's the idea, yes?
Yes, so how would you, so this, the error probability being 2 into the R minus E is Shannon's theorem, right?
Yes, this is the essence of Shannon noisy channel theorems. It tells you that if you have a channel with capacity C and you transfer with the rate R, this is your probability of error.
Do you have a proof?
Yes.
Will we cover that now?
No, absolutely not. Yeah, I'm not proving anything in this course, right? And some proofs I do know, I like. Some proofs I don't know, I don't like. But it's, what I definitely know is that I'm not a mathematician. And so I'm not trying to do some things which, but I'll, in my lecture notes, I'll give you places and references where you can find them. And they aren't that kind of complicated. I just, you know, I want to tell you about quantum teleportation, black holes, theory of mind. I want to see you panoramic picture, because all this, it's, I mean, communication theory is a whole semester course in a trivial case and 1 year course in a mock case. I've shown you Huffman codes. You remember we had four things, and we, Huffman codes is a subject of at least a month of lecturing. I mean, this is unbelievably beautiful mathematical subject. I spent on it like half an hour. So you must understand what kind of course you're taking, right? It's things which just I'm telling you what are there, and I'm telling you that as a physicist you are well ready to take it, because it's mostly use P log P, and today we also learn unbelievably complicated formula which is P log Q, and that's F equal E minus Ts. That's all there is, right? But in a very, very sophisticated way they use it. But It's our language. We invented it, right? Okay. If this is okay, more questions? Yes.
And just a thought. So we saw the first thing you started with was the Carnot machine, which you showed us has a fixed value that it can work. Can this be related to somehow analog of a Carnot?
Yes, yes, we'll come to it. In a sense, that's what I guess Landauer said, that we started from understanding what restrictions are imposed on engines, on thermal machines, or refrigerator or engines, right? Then we moved next step and we started to ask what restrictions are imposed on communications. That's what I'm doing right now. Then we made next step, as this we are moving from early 19th century, late 18th to 20th century, first part. Then we started to ask what restrictions are imposed on computations. And they all used the same entropy, or making it more and more sophisticated, right? Boltzmann did not know about mutual information and did not use it. It would save him many sleepless nights if he would be able to look at his difference between sum of entropy of individual particles and the entropy of whole system, and understand that this difference is mutual information. And of course, it's natural that it grows. They collide after all and interact. Okay, so this is essentially our progress in going from engines to communications to computation and to brain, how actually it works. Okay, but it's more or less always the same question: what restrictions are imposed by our partial knowledge? Entropy, in essence, quantifies our partial knowledge. But now you see how it turns stable. Now it quantifies our rate of information transfer. Because the more you don't know, the more information every message brings. Okay? Good. Now I want really to consider something somewhat technical, but necessarily, because, as I said, we are in the domain of discrete, right? So we were doing flows, you remember all this. But to do information theory, you need to count. But I mean, noises in electrical signals, they aren't discrete, right? They are usually analogous devices. And so we have, in our optical devices aren't discrete, they're usually continuous, etc. So we need somehow to handle continuous functions. And need to able to work with information theory objects when our functions are continuous. So how to do it? If I'm interested in getting information about position of a particle on an interval L, how much information I need to set a position? You wanted to say something, right?
Exactly, are we allowing it to
Exactly, real number.
can't specify, it takes an infinite.
It is infinite, right? So this is just an infinite, even if it's just a rational number, there's infinite amount of rational numbers here, right? Which means that, technically speaking, it's meaningless. So what I really need to do, I need somehow to make this continuous problem discrete. I'm saying, I mean, look, I don't have such a ruler or whatever measuring device that can work better than epsilon. So I would say that this would be all with epsilon precision. So if you just tell me in which of these epsilon intervals my particle is, that would be what I want to know. And now, what is the information which is position will bring me? It's just log 2L over epsilon bits, right? So this is the maximal information one can get out of it, assuming that these all intervals are equally probable, and this is the maximal it is, okay? So, which means that if you are this is the, let's say, S of B equal to it, right? And now I may say that this information which is brought is something which is how I would so this is S of B under A. No. This I actually wanted to say something. This is the next step. Okay. So S of B, this S of B. Now what I want to do, I want to say that my measurement A has a precision delta. Okay. So now on B, particles are whatever, I don't know. There is your unit cell in a crystal or whatever. But I measure A with something else, with a precision delta. So now, if what I'm interested in, to know what will be the mutual information between A and B, or what would be a capacity. So I would say that this is S of B minus S of B under A. Okay? So now, if I get A, then I would get my position of a particle within delta, right? So this is log L over epsilon, and what is this? Huh? And most of the present-day quantum field theory actually comes out of this simple formula. What is beautiful about this trivial formula? There is no epsilon here, right? Which means that when epsilon goes to 0, this goes to infinity, and this goes to infinity. You need infinite amount of information to set this or to set this. But mutual information stays finite. Okay? This is really important. So you have your precision, resolution, whatever, and entropy always has a logarithm of this epsilon as an additive constant. But in mutual information, because it's a difference, and the same happens with entanglement entropy in quantum statistics, as we will see. Everything related to small scales, or as field theoretical people like to say, all ultraviolet details, all your crystal lattice details, whatever you have a small scale, it disappears. That's why we so much like this object, that it really totally insensitive. There is question? No.
The kernel of this map.
Huh?
Like the precision is like the. Never mind.
Okay, yeah, but if there is something interesting, then you can share it with us, and we can. If it's not interesting, no reason to talk about it. If it's interesting, I mean, I as much want to, that's. Okay.
Well, I've seen a treatment of this where it's like you map from the space of A to the space of B, and you can think of the precision as the size of the kernel of the map, and then the quotient space gives you the size of the mutual.
Yes, this is one way of looking into it, that you are doing transformation from one to another. In this transformation, let's say from rho of x, you go to rho of y. And so you say rho of x is some k, x minus y, rho of y. And this kernel k can have some window. Okay? Could be, and then you can treat it as a resolution. Okay, now this more or less suggests how to work now, not with, here was a constant distribution, but imagine we indeed have some distribution which is rho of x. X is a continuous variable, okay? But we know how to define entropy or whatever only for, let me write entropy somewhere. So what I now want to do is to take S equal minus pi sum over I pi log pi, and replace it by an integral. Go into a limit, and I would say that my pi is actually expression of some rho of x I times epsilon. Okay, so I kind of mentally assume that I would then I can turn it in a continuous limit in the following sense. It will be rho of x logarithm. So this would be rho epsilon, which I would replace by dx. This would be rho epsilon. Then this sum I would replace as an integral xi dxi. This is my epsilon shrinking to 0 and replacing as a differential. So that will be this logarithm rho of x plus log 2 of 1 over epsilon, right? So again, there is no escaping the fact that if you have a continuous distribution, then in the limit it goes to infinity. But this is a perfectly final part now. It's not the entropy. It's what is called differential entropy. But in a sense, we'll be working with it, and it will be telling us mostly what we need to know. Because again, when we'll be working with the continuous channels, we will be interested in capacity. And capacity is a mutual information, and it does not care about it. So we'll be perfectly able to use it. Let's compute a differential entropy of a Gaussian channel. So let's take the probability of noise. Noise will be always this Greek letter psi, and it would have a variance which I would call n because it's noise. So it will be capital N, and it will be exponent minus psi squared over 2n. Okay? So this is p of psi. Now if I plug it into rho of psi, yeah? And so now if I plug it into this formula, I would obtain S of psi equal to minus from infinity to infinity d psi of psi log I'll do logarithm, right? I know I can do log. Yeah, it does not matter. P. So what you'll get log of this times p, which is just gives you this constant, and then when you take log of the exponent, it would give you this, and when you compute it essentially would be psi squared integrated with psi, which would give you n, right? So it would give you 1/2. So essentially what you would obtain 1/2 log 2 pi e n. Right. Yeah, because here you have E, then you would have this. Okay, this is the entropy of so-called Gaussian distribution, and now we are ready to treat what is called Gaussian channel. Okay, so what will be Gaussian channel? This now we apply all our combinatorics into really continuous. Now this is already electrical engineering. So we say that A is B plus psi. Psi is whatever we say. Now, if B is just a signal which is dynamic and not statistic, then it's clear that the only statistics here is the statistics of psi, and then there is a probability, the entropy of A is the statistics of psi. But generally, let us consider it a more general situation. So the B could also come from any distribution. And first, let's compute what is the probability of B of A given value of B. So let's say B is given. But it will be, for now it's dynamical variable. So B is given. What is the probability of having A? It must be expressed in terms of B, right? B is now is a given number. And A. But I know probability of Xi, which is what in terms of A and B? Yeah, it's A minus, absolutely, yeah. A minus B. And probability of this, I know it is this. And it's expressed in terms of A and B. So it's exactly what we need. So the probability of given A, given B, is their difference, Gaussian distribution of their difference, right? Because this is exactly the noise. So we can write it that this is 1 square root of 2 pi n exponent of minus A minus B squared over 2n. Good. Now, this is for a given B. Now, imagine that we also have a statistics of B. Yeah, oh, here it is. And again, that could be different statistics of B. We can take uniform statistic on an interval, etc., which is all the cases which are meaningful and interesting. But again, the simplest case, let's say that we have P of B, also Gaussian, but with something which we call S, right? I call it S, yeah, S, because it's a signal. So I want it to be S. So my P of B is exponent minus B squared over 2S. Now I'm ready to compute probability, let's say, of A. How I compute probability of A? Okay, yeah. So I have probability of B, probability of Xi, this. A is their sum. How I get the probability of A out of it? Yes? Yeah. I need to integrate over all values of B, integrate over all values of Xi. They're independent, right? I assume that the noise is independent on a signal. So it will be P of B, P of Xi, but I need to account for this with the delta function of A minus B minus Xi. It is as simple as that. And I spare you Gaussian integration and write you the answer, which is non-surprisingly will be given by n plus s. It's a distribution because they are independent signals, then they with mean 0, they are just variances add to each other, and you get 1 square root of 2 pi n plus s exponent minus a squared 2n plus s, but you check it, right? Just, all such things. Now,
like how the n and s are like given in this situation. Like
n is an amplitude of noise,
okay.
variance of noise. Okay, s is a variance of b.
So we know those information.
We know that my signal comes out with this average amplitude, and we know that noise come out with this average amplitude. But by itself, any given value of B or Xi, it's taken out of this distribution. But I obtain A, so I would like to know how much. Now, if I'm interested, so you see, we know 3 out of 4 guys that we need. So we know P of B, P of A over B. How now you get what you really need? Probability of input under a given signal. So the signal sent was B, but we obtain A. So what we need for our measurement is a probability of B under a given A, right? And I've prepared everything to get it. So how now I compute what any communication, measurement, or whatever need? What is the probability of input under a given output? How I do it? What formula, basic formula from which we started today? Huh? It's bias formula, right? But I did not define bias formula yet. It's also just a chain rule. Bias formula is nothing but a chain rule. You remember the chain rule? Let me remind you the chain rules with which we started today's lecture. It's that P of A of B is P of A of B, P of B. It's P of B conditional on A, on P on A. Right? So now, if you really need this, what you need to do, P of B of A, you need to take P of B, this guy, multiply P of A of B, and divide by P of A. In the second part of today's lecture, we'll be calling it bias formula, but for now it's just, so now can really we see how this communication or measuring channel works. And again, this is now not even an integration. You just take this, you take this, and you take that, and you just take this two with a plus in the exponent and this with a minus. And what you've got is the following thing. You want me to do the computation in more detail? Yeah, I guess it's just summing things in the exponent, n of s divided by 2n. And the exponent is actually interesting. First of all, its magnitude, and what stays here is b minus a s plus n squared. As they say, whatever computation you do, stop and reflect. Okay. So first of all, this is a really working device. You get A equal to 5. That's your probability of B, right? It's definitely now has a mean value, right? Out of this distribution, by the way, we can compute the mean value, right? It's an integral over dB, mean value under a given A. So now our distribution is shifted by a measured quantity, right? So it's B, P of B of A. And again, I spare you this simple computation is A S plus N. Okay? What is, if you look at this formula and you look at this formula, what strikes you? What is the meaning of it? How would you interpret it? This is you measured. That's your best prediction for what is actually you've measured, right? Sometimes people divide it by n and write it as A SNR 1 plus SNR. That's the way engineers use it. It's called signal noise ratio, S over N, right? So that's why I use notation SN. So again, when your signal, when your noise is very small, that's trivial, right? B is just A. What is interesting that when noise is large, you still have a linear relation between B and A. I don't want to go into much computation to show you that this is a specificity of not only linear relation here, but Gaussianity here. But if you are interested in it, go and check that if you take another trivial distribution for B, for example, exponential or uniform, linearity will be lost. This linearity is a property of Gaussian distribution, which some variances and of linearity of a dynamical relation that your noise is additive, right? But it tells you divide it by a big number. If your noise is large, don't think that your A is your B is equal to A. It is probably much smaller. Most of what you measure is noise. And it tells you how you divide it by noise variance. S over n, right? When n is large, its signal to noise ratio. So when the signal to noise ratio decreases, it's your prediction for what you actually measure. You understand that what you're measuring is essentially noise, right? Okay, so this is, so you see, we used this formalism of conditional probabilities, etc. And of course, the capacity of it is, we now can compute, it's a mutual information between them. Even though entropies are infinite, technically speaking, right? If you try to treat entropy of a continuous distribution, it's infinite. But by using this differential entropy, it's still perfectly meaningful consideration, right? So any question about Gaussian channel so far? Okay, then let's compute its mutual information. So its mutual information, any prediction, mutual information in terms of bits. How many, first of all, again, you know, you're a physicist, right? Which means that whatever you start solving the problem, you first close your eyes and try to imagine what, how answer would look like, first in particular which letters it will contain. Suggestion.
A guess might be something like a log of the signal noise ratio.
First of all, it must contain S and N. There are no other numbers, right? We're physicists, right? So first we ask what will come into the answer. Then we ask what is the dimensionality of things. This is the second thing which any physicist asks, right? What is the dimensionality? Well, this is bits, which means dimensionless. Well, this is watts. So S over N, that's for sure. Like gentlemen suggest, it must be S over N, signal to noise ratio, right? Now, okay, what your suggestion was log. Log of signal to noise ratio, log of 1 over signal to noise ratio. You must, you know, any initiative is punishable. So your initiative, now you are responsible for it. If you take logarithm of S over N, when signal goes to 0, it would go to minus infinity. When signal goes to infinity, it goes, something is wrong here, right? Logarithm is a dangerous function. So how to remedy it? 1 minus plus. This is good. I mean, it's so the suggestion is like this. So when signal goes to 0, would be 0. That makes sense. When signal to noise going to infinity would be logarithm of, yeah, right. So this is my signal, this is my noise. Signal over noise is how many actually values of signal I distinguish. Boltzmann entropy, right? So let's compute it. Okay, good. Where is my eraser? Yeah, here it is. Yeah, but look, I mean, physicists always work like this. You never do computation before you predict what you're going to. I mean, our brain works like this, and we are trained to do it. So first of all, and then when you make a mistake, then you, and when you really get an answer and it's different from what was your prediction, you learned a lot of the ways that you think wrongly, right? So always make prediction. Never start any computation without predicting how the answer would look like, right? Yes?
I think I'm not following the intuition over there. So like, I just want to clarify the like physical meaning of the like mutual information once again. So
Mutual information tells me how much, it's actually capacity of a channel, how much such channel let me to get information. Let me remind you what is a channel. There is something coming with amplitude of a signal, but noise added to it. And I'm asking how much I can read from this value about this. Okay? This will be my mutual information between A and B. To get it, let's now compute it, right? Because hand waving, arguments, dimensional arguments, symmetry, all this is all good when you know the answer. but when you don't, you go and compute. So let's compute it. So fortunately, I mean, we have the whole enchilada of, we can compute it both ways, right? So it's, let's say, S of A minus S of A B, right? Let me do it in a little bit sophisticated way just to show, this is also the way of argument which mathematicians always use in proving theorems. So I won't prove theorems, but I'll show you at least the techniques that you use. So what is A? You remember that A is actually, but so it's S of A, which we need to compute it, it's over there, but it's minus S B plus C conditioned over B, right? So this is my A, right? Now, of course, B and B have zero entropy in between themselves, and of course, the S entropy of Xi conditioned on B is just entropy of Xi. It does not care about B. They are independent. So what I will get a simply S of A minus S of Xi. S of Xi we were happy to compute before. Here it is. All right. S of A would be the same, just it's, you know, for any Gaussian statistics, the entropy is a logarithm of variance with a constant 2 pi e, which I always drop and which sometimes you need to keep. But essentially, it tells us that this would be log 2, and what comes from here, n plus s, and what comes from here is n, and this is, of course, logarithm 2, 1 plus s of n. So you were right, and this is exactly what we observe. And now this is, yeah, what I did wrong here is 1/2. 1/2. This is, by the way, something that you won't get by arguments like this, right? Because it must be 1/2 because it is this 1/2. It's always 1/2. But it's essentially 1/2 because our n's and s's are variances. They're squares. So if you would treat it in terms of, this is not an amplitude, this is amplitude square, and this is amplitude square. Yes?
When we deal with these things, why do we call these signal and, or why do we use the term signal and noise to refer to variances rather than signal and noise referring to standard deviations?
I don't know. Physicists would probably call signal to noise square roots of it, namely amplitudes. But it's all originate from communication engineering during mid-century, World War II. That's where it started. So now we're just stuck with it. I mean, this is a standard notation. That's why it makes it 1/2 here, which means that eventually, in the limit when this is very large, this is indeed the logarithm of amplitude signal, amplitude noise, not variance, which is more or less Boltzmann, right? Yes.
I suspect it might be because in physics the power is usually the square of the amplitude. So by using the signal to noise as variances as the squares, that would be like the signal power and the noise power.
Yeah, they always measure, you know, opticians measure intensity. I mean, nobody works with amplitudes. They always work with intensity, with powers. Okay, good. So it's natural time to make a break. Any questions for now? Okay, let's make a break. 10, 15 minutes. How long you want your breaks? It's up to you. Okay. Okay, 15. What? Or you want? If you want to finish earlier, then we can make shorter break. Or you want to go without a break, just non-stop? Because I know I will start a new chapter, so I would rather make a break. Okay, so let's have 10 minutes break. Okay. Good.